here, it will decoherent here. If you prepare a minus state, it will decohere to plus state. This is called phase decoherence, and this is called relaxation. So this lifetime of qubits are like typically in few milliseconds. For example, for superconducting architecture, it is 1 millisecond, and trapped ion, it is around 10 milliseconds. But if you think about like some important quantum algorithm like factoring a 2048 bit integer using source factoring algorithm, it will take with current technology and current codes, it will take typically 7 days, and it requires around 1 million physical qubits. So how do like but if you look at the current architecture, the lifetime of a physical qubit is few milliseconds. So how does one prolong this lifetime? So one can use quantum error correcting codes and encode one logical qubit into many physical qubit. I'll come to it what I mean by encoding one logical qubit into many physical qubits. But basically, the error correcting code should have these two property. It should minimize physical qubits per logical qubits, and it should have high distance. High distance is useful in suppressing errors, and that would in turn increase the qubit lifetime. So I am aware that you guys have heard about this stabilizer codes already a few times. But I'll just give a brief introduction. So there are kind of like four matrices: this I, X, G, and Y. They're 2 by 2 complex matrices, and uh, uh, these matrices, like you can use these matrices to define something called a n-fold polygroup. So this polygroup would contain operators which are like n-fold tensor product of these polymatrices. And you define a encoded state. So you define a stabilizer code by choosing a subgroup of this polygroup. In fact, a abelian subgroup of subgroup of this n-fold polygroup, and then the coded states are defined as the +1 eigenspace of this subgroup S. So basically, you are trying to stabilize the qubit. So let's look at an example. Let's consider this subgroup S, which has two operators, G1 times G2. Here, this stabilizer acts on the third qubit trivially. So it's identity. So I'm first and second qubit, it acts like this G matrix acts. Then the second one, let's say, is G2 and G3. Then if you look at the common eigenspace of this these two matrices or two operators, you'll see they would be of this form, this psi L. There would be, so the logical code word would be of form. So how do like I have this code, then I should be able to detect if some qubit goes to error.
Yeah, just
So
a doubt. Just a doubt. Can you just go to the previous slide? So the Z1, Z2, which, so they are the polymatrices, huh? The Z1, Z2, Z3. Are they the polymatrices?
So that this tensor product of these polymatrices. So like it is Z1 tensor Z2, then the other operator is Z2 tensor Z3. So
Okay.
one of them is a 4 times 4 matrix, the other one is also 4 times 4 matrix. So you take this two 4 times 4 matrix, and so they'll have 4 eigenvectors, right? With 4 different eigenvalues. You just uh, uh, choose the common eigenvector with +1 eigenvalue.
Okay. Okay.
Right. So now you Uh, so how do you use this? So this is called a bit flip code. It has distance 3, and it can correct one bit flip, or like one qubit flip. Like if the qubit goes from 0 to 1 or either 1 to 0, it would be able to detect and correct it. So how do you first check if the code word is in error? So you do something called this syndrome extraction. So I have two generators, stabilizers, two operators here, G1 times G2 and this G2 tensor G3. So I would choose two ancillas and assign them to 0 here. Then I'll measure these two stabilizers. As these stabilizers kind of stabilize the code word space, by measuring them, I won't change the encoded information if it is not erroneous. So how do you measure this? So for each operator GI in the stabilizer, apply a CNOT gate with ith qubit as control, and the corresponding ancilla as target. So for example, take this G1 tensor G2, it has a G1. So you take this qubit Q1 and do a CNOT with this ancilla. Similarly, take G2 and do a CNOT between qubit Q2 and uh, the this is the third CNOT. Similarly, you do for the other operator. This much is the circuit is clear.
Yes.
So
Yes. Yeah.
I'll assume it's clear and I'll proceed. So let's say the qubit Q1 or the fast qubit goes through a bit flip error, means a polymatrix X is X acts on it. Let's see what happens to this syndrome bits. So so you can commute this a polymatrix X tensor I with the C naught gate like this. So at the beginning, at the input of the C naught, you have X and I. So if I commute it, it will at the output it will basically become X and X. And the other qubits are not error free. So if I track this error, so this it will be here at this fast ancilla. So it will flip this ancilla from 0 to 1, and I'll have a syndrome 1 0. And my error estimate would be on the 3 qubit would be XII. If there are no error, I'll just observe syndrome 0 0, and my error estimate would be III. I can apply this logic and fill this syndrome table. So for each one qubit bit flip error, I can correctly estimate the error and then apply the correction to bring it back to its original state. So, so the point is this bit flip code can correct one error, one bit flip error. Uh, so this all fine. This in principle shows that you can correct quantum errors, but I mean this can just correct one bit flip error. So how do you scale it? Like how do you correct phase flip errors? How do you correct? How do you correct more errors? So so for this one need to design this this stabilizer group carefully, right? So in around late 1990s, Calder Bank, Shore, and Steen related this this quantum stabilizer codes to classical codes and made this designing these codes the job of designing these codes easy. So to do so, they figured out there is an isomorphism between the poly group to this F2, like length 2 vector from poly group to length 2 vector. Here the identity is mapped to 0, 0. The X matrix is mapped to 1, 0, and Y is mapped to 1, 1, and G is mapped to 0, 1. So this mapping kind of also preserve the group operation, right? Like if you multiply uh, two polymatrices X and G, you should get Y. And in this case, if you add these binary tuples corresponding to X and G, you'll see that you'll get Y. So let's look at an example. So let's look at this stabilizer group. So it has like 6 stabilizers. So let's map them to their binary form. So this let's consider this first one, which has x4, x5, x6, x7. So this x, each x is mapped to a 1 and a 0. So in the first operator, this x4, x5, x6, x7 doesn't have any g. So the g part of it would be, so the first part kind of represent the x part, and the second column, this hx and 0, this first block kind of represent the x part, the other part, the second block represent the g part. So here the hx and hg are given. So like here, if you look at the first row, it has ones in fourth, fifth, sixth, and seventh position, because x4, x5, x6, x7, uh, the first operator is x4, x5, x6, x7. Then you can similarly see that uh, the second row is the second row corresponds to x2, x3, x6, x7. Similarly, third row, you can also see hg similarly you can also figure out hg, and you will figure out this hx and hg are same. So given two classical parity check matrix hx and hg, if they satisfy this condition, then you can map them to a stabilizer group, given they of course satisfy this condition. I'll stop here for a minute and see if anyone wants to ask something. Okay, so I'll go ahead, and then you define the logical operators as this. So this cx is the code book corresponding to this parity check matrix hx, and cg is the code book corresponding to the parity check matrix sg, and this cg pop and scx pops are like orthogonal codes of cg and cx. So the logical operator is defined as this. For this example, the logical operators is given by uh, it has only one logical operator and it is given by this guy. So you can see you can find out these logical operators by basically looking at code words of h of x and h of g. In this case, if you see this logical operator is orthogonal to uh, all three rows, and the distance of the code is defined as weight of the minimum weight logical operator. In this case, this logical operator has Hamming weight 3, so the distance of the code is 3. So why do we need this is all fine given now given a dual containing classical code. By dual containing, I meant if they satisfy this condition, you can always derive a quantum code. Uh, so all this is fine, but then why do you need uh, quantum low density parity check codes? So let's go back to the syndrome extraction circuit I had initially, and let's look at it again. So this F here represent possible errors. It takes value from one of the. It can be one of the polymatrices. So in between, if you see, I'm introducing more error. So that is because at a time, a qubit can be involved in only one gate. So at a time, you can, for example, do execute this CNOT gates parallelly. Once this is done, you execute these two CNOT gates. But between this two-step execution, time has lapsed and there would be more error. So these in between errors are uh, introduced to account for this this extra error due to this extra time between this execution of two sets of C nodes. So basically, this if this is a depth 2 syndrome extraction circuit, so I'm introducing error twice. If it has depth uh, uh, larger depth, then more errors should be introduced, and this kind of depth is determined by the density of the parity check matrix. Basically, it says how many time steps you need to execute all the C nodes. So more time steps is kind of more error. So if you have a sparse parity check matrix, then the error decreases. So it is crucial to have low density parity check matrices. Then there is another requirement, that is like this need for fast decoders. At the beginning, I said that these qubits have very low um, lifetime, right? So before they decohere or before the information becomes meaningless, you should be able to extract your syndrome. Then you should be able to decode and apply the recovery operation. So here, this is kind of a syndrome extraction circuit. You decode, then you apply this recovery, then you do again syndrome extraction, then you decode, apply again the recovery. So if either your syndrome extraction is not fast enough or the decoder is not fast enough, then the by the time your decoding is over, the qubit physical qubit would have become already meaningless. So one need to ensure that the measurement is fast and the decoding is also fast. Typically, the decoding time should be less than measurement time. So by the time the measurement is done, the decoding also uh, should be done. And the fast measurement time is ensured by having this low density parity check matrix, and uh, the faster decoding, you hope that have this quantum LDPC code, and since they are similar to classical LDPC code, then you would have faster decoder for them because we already have faster decoder for classical LDPC codes. So the objective here is to kind of construct families of QLDPC code with distance growing linearly in the number of qubits under a fixed logical to physical qubit ratio. This distance growing linearly because you want more distance so you can suppress the error more, and this fixed logical to physical qubit ratio is required to keep the overhead in check. Then you should also have fast decoder for such QLDPC codes. But constructing these codes are this QLDPC codes are not easy. It was kind of a open problem for a decade. Uh, so why is it difficult to design these LDPC codes? Uh, these are for because of this is because of the following two reasons. So as I said, you want the row weights of h of x and h of g to be small, but you want the minimum distance to be large. So, and these two codes should satisfy this condition. So because they should satisfy this condition, you can see that h of g should be contained in the uh, x code, and h of x should be contained in the g code. So the minimum distance is kind of determined by the lowest weight code word in C of x, but so you want to increase the weight of the lowest weight code word in x, but it contains h of g, and you want the row weight of h of g to be uh, small at the same time. So this is kind of like a little contradicting. That's why people were not able to find good QLDPC codes for a long time. Uh, then finally in 2014, Tillich and Jemma proposed a construction which is called hypergraph product codes, and uh, the distance of these codes grows with square root of block length. Then followed by that, there is like a new family of code, which is like for that code, the distance grows linearly, like almost linearly with block length. Uh, so is it all done, then like we have the codes. So we have low density codes, and the distance already grows linearly. Then what is the problem? Is the code construction part is solved? Not yet, because um, uh, mainly there are many reasons, because there are mainly two reasons. Uh, so one is uh, the these two hypergraph product codes and limited product codes kind of allows arbitrary parity check matrices, but the current physical hardware do not support this arbitrary parity check matrix. It allows only uh, like this geometrical locality, meaning um, uh, if you arrange the qubits in a two dimensional grid, the a stabilizer can only operate in like uh, qubits which are next to each other. So for this reason, these codes are not applicable for like, for example, superconducting platforms. So group of people from IBM proposed this bivariate bicycle codes, and they kind of the distance is not like linear with block length, but they shoots that the platform IBM has. Then the other problem is constructing fault tolerant gates that support uh, 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 universal computation. I think in the next session, Narayanan will talk more about fault tolerant computation. So let's look at one of these construction. So how do you construct this hypergraph product code? So you take two classical parity check matrix H1 and H2, and then using this tensor product, you construct two separate matrices Hx and Hg, and this Hx and Hg would define a CSS code only when they satisfy this condition Hx times Hg transpose is 0, and you see here they satisfy that condition. So block length of this code should be, if you start with two parity check matrices, classical parity check matrices of dimension m times n, the block length of the resulting code would be n square plus m square, and the logical qubits would be n square plus m square minus 2 times m times 2mn. So this m times n comes because this hx has m times n rows, and hg has m times n rows, and the distance of this code should be minimum of t1 and t2. Here t1 is the distance corresponding to the classical uh, parity check matrix H1, and D2 is the distance corresponding to classical parity check matrix H2. So you see here the distance kind of grows uh, uh, as square root of the block length. So next I'm going to talk about graphical construction of this this hypergraph product codes. For that, I need this graphical representation of graphical representation of this classical parity check matrix. So let's consider this parity check matrix, all one parity check matrix H. This is the graphical representation, or what they call graph of this parity check matrix H. So here the circles represents the circles represent the column of this parity check matrix, and the squares represent the rows of the parity check matrix. So this check nodes kind of impose a constant on these variable nodes, and there is an is between the ith variable node and jth check node if the ijth element of this parity check matrix is 1. So it's all one matrix. So there is a, like, every variable node is connected to every check node here. So let's say I have two such classical graph. Here is one is here and the other one is here. How do I obtain the graph corresponding to the hypergraph product code? So let's see if I can pass this slide. So you take graph product of this graph. This is corresponding to, let's say, the classical parity check matrix H1. Then the second graph, let's say, corresponds to parity check matrix H2. Then you do graph product. In graph product, you multiply a variable node with a variable node, you get a BV type variable node. Then you multiply a check node with a check node from code 1 to with a check node from code 2, you get a CC type variable node. Basically, this BV and CC type variable nodes in this bigger graph represent qubits. Then you multiply a check node with a variable node. You get these resulting nodes are represented by a square with a circle inside, and they represent this X type stabilizers or X type checks. Similarly, you multiply a variable node with a check node, you get a G type stabilizer, and they're represented by a square, a circle which has a square inside. So how do you, like, let's say you take this variable node here and multiply it with a variable node from here. So how do you define the uh, connection, the, like, the set of, let's say, nodes connected to this BV type variable node? So you see this variable node is connected to this check node and this check node. So this BV type variable node would be is connected to here, this X type check and this X type check. Similarly, it is also connected to this G type check or Z type check, because this variable node is connected to this check node. So basically, you can obtain these connections from the connections in the hypergraph product anagram, from the connection from the parent graph. So now here, let's look at, so here some edges I have highlighted in red, some are highlighted in black. So let's look at them separately. So basically, the black, the red edges corresponds to the tanograph corresponding to parity check matrix H of X, and the black edges corresponds to the tanograph corresponding to the parity check matrix GG. So one thing here to note is that like this parity check matrix here is getting this parity check matrix is getting repeated multiple times in the resulting graph. Similarly, if you see this tanograph also is getting repeated in the resulting tanograph. So you have like multiple copies of the classical code in the hypergraph, like multiple copies of the tanagraphs of classical code in the tanograph corresponding to hypergraph product code. So this would be useful when we talk about decoding, like designing decoders for these hypergraph LDPC codes. So now let's go back again to the classical codes. So these classical codes do not do not do well if they have uh, like this kind of structures, this kind of small cycles in the tanograph. So this is a 4,4 trapping sets because it has 4 variable nodes, 4 circles, and 4 odd number check nodes. Here there are 4 odd number check nodes. So these trapping sets are composed of small cycles. They are kind of contained in the support of a code word. So typically the low complexity iterative decoders fail to converge when the error pattern lies on these uh, trapping sets. So they're generally addressed by designing decoders such that these small cycles are not there. Uh, if they're there, then that like handled by carefully designing the decoder or modifying these iterative decoders. So let's go back to our hypergraph product. So let's take, so as I was saying, you obtain this hypergraph product code by taking graph product of two classical code. So you just taken instead of looking at the whole product, you just look at take a check node from the code 2 and take a variable node from the variable node from code 1 and see and multiply them. So this check node has 4 variable nodes and this variable node has 3 check nodes. So if you multiply them, you will get a structure like this. So here this the red edges are shown are corresponds to a CB type stabilizer, or this is like corresponds to X check, and all the black edges corresponds to uh, G checks. So if you see, there are many cycles, small cycles here. If you remove these red edges, so when the error, when you are decoding, let's say H of G, and error lies in the support of a X check. Here is the X check. Then the decoder doesn't um, converge. Uh, in the current literature, these trapping sets are avoided by using some BP and then a post-processing decoder called order statistics decoder. But the problem with such decoders is like it is extremely complex.
ஏன்பா ஏதோ சத்தம் கேட்டு
So it is extremely complex. To be precise, the complexity grows polynomially with block length. So the question is, can we avoid this complexity? So before going into complexity, let's see why these are like uh, these trapping sets are hard to resolve. So I have removed the red edges. So let's consider decoding this trapping set. So let's put here the variable nodes are uh, if so every node has like two shapes. If the shapes match, they are the variable node. If the shapes do not match, then they represent check nodes. So variable nodes corresponds to the qubits, and the check nodes corresponds to stabilizer. So let's say this uh, the square variable nodes are erroneous. They're represented, so their inner shape is in black to show they're erroneous. So if these three variable nodes are erroneous, then their neighboring checks are uh, the neighboring checks are unsatisfied. So let's consider a decoder that kind of keeps initialize the error estimate to be all zero. So initially the decoder is saying none of these are erroneous. Then based on these unsatisfied checks, it will try to modify the error estimate and see if it can converge. So what does the decoder do? Decoder flips the error estimates if it finds a variable node is connected to uh, all unsatisfied checks, meaning the neighboring, if all the neighboring check nodes of a variable node is connected to unsatisfied checks, then the error estimate on it should be flipped. So here all these three variable nodes are connected to all their neighboring checks are unsatisfied. Same is true for all these circle variable nodes, VV type variable nodes. As a result, the decoder will flip the error estimate on all the variable nodes, all seven variable nodes, both square and circle. So if it flips the error estimate on all these variable nodes, in the next iteration, uh, it kind of correctly estimates the error on the square variable nodes. So uh, I have so they are now shown in white, but it wrongly initially when started the circle variable nodes were not erroneous, but the decoder predicts them as erroneous. Now, as these circle nodes are erroneous, all the check nodes in this subgraph are also unsatisfied. As a result, all the variable nodes, like every variable, the neighboring check of the neighboring checks of each of these variable nodes are connected to are unsatisfied. As a result, the decoder is going to again flip the error estimates on all the variable nodes. So we are back to the initial error. We are back to the initial condition. We started where uh, the square variable nodes were erroneous, and and all the check nodes are unsatisfied. We are back to the same problem. So the decoder is going to oscillate without converging. So how to handle this um, how to handle this kind of errors when this kind of trapping sets. So let's look at a different decoder. So earlier in the previous decoder, we flipped the error estimate on the square nodes and the circle variable nodes at the same time. Instead of that, let's flip them alternatively. First, let's so here so let's start by first flipping the error estimates on circle nodes. Then we'll flip the error estimates on the square variable node or CC type variable node. So let's say these two CC type variable nodes are in error. As a result, these 8 checks are unsatisfied. So now in the first iteration, we are going to flip the error estimates on BV type variable nodes. So all these VV type variable nodes are connected to more than two unsatisfied checks. So we'll flip the error estimate on them, and after flipping the error estimate on, okay, there is an error in the iteration 2. This node would be non-erroneous. Then in the next cycle, next iteration, you flip the error on uh, this third CC type variable node, uh, and you'll see that now all the checks are satisfied. So initially the error was on this two CC type variable nodes, but at the end we saw that the mismatched error, that is the error estimate plus the initial error, if you add them together, then the mismatch error is on all the variable nodes. But this is fine because this is we saw that uh, these all these variable nodes uh, lies on the support of a stabilizer. So this is so basically the decoder converges to a stabilizer, and we are fine. So what we are able to do is, like, by changing the schedule, uh, by studying the decoding dynamics, we figured out if we change the schedule, meaning if we update the error estimates on these two type of variable nodes alternatively, then we can resolve these trapping sets. So there are also other type of trapping sets. As I said, the classical codes also has trapping sets. So let's here is a 4,4 trapping set. So when you take graph product, this trapping set is going to be repeated multiple times. Here it is being repeated uh, twice. Uh, it's being repeated twice. So these trapping sets can be handled by looking at the classical error correction literature and looking at the decoders that can resolve this one. Then from there you can derive decoders that can resolve these um, uh, inherited trapping sets. So with this, there is this simulation result. Here we simulate a hypergraph product code, and we simulated three decoders: the scheduled min-sum decoders, that and then another normalized min-sum decoder, and this PP plus OST, which is the complex decoder. The scheduled and min-sum decoder should be able to decode the stabilizer induced trapping sets. So as you can see, that is reflected in the performance. This scheduled decoder would has like a order of magnitude performance improvement over the other two um, the other two decoders. I think I'll stop here and take questions.
I just have one question. So in the classical communication, we know the Shannon's capacity has to be achieved, and we have all these different coding techniques to achieve it with arbitrarily low probability of error, right? So similarly, in
Yeah.
the quantum field, what would be that capacity that what is it? How do we define that? What is the capacity
So,
we want to achieve using these codes and all that?
sure, sure. So that notion is very difficult to define in these codes. So the capacity, so there are two issues to here, right? So the capacity analysis of classical LDPC codes um, uh, relies on the fact that there are no short cycles in the Tanner. But in quantum LDPC codes, by construction, they'll have this short cycles. In particular, they'll have cycles of length 8, and this like density evolution analysis where you kind of um, obtain the threshold of this classical LDPC codes won't work here. Mm. So there is no such notions of at least people have not done that. The other fact is one thing I didn't mention here. Let me go back. So you see the syndrome extraction circuits, right? Uh, in the syndrome extraction circuits, I have assumed here that these C0 gates are perfect, meaning like they behave as expected. But that is not the case in practice. So they will behave expectedly only with some probability. Let's say they behave expectedly with probability 1 minus p, and with probability p, after their execution they'll introduce error, uh, and they can introduce error in both the qubits involved. So there are so many of these C0 gates, and each of them can fail and can introduce errors, right? So the error correction, like when you are extracting this syndrome, you are introducing again new errors. So it is not like just because you have a code with good distance doesn't mean that it will do well in this quantum setting because of this C0 failures during syndrome extraction. In classical, if in classical syndrome extraction, have you don't have this erroneous, right? You do this kind of like the equivalent of C0 gates using software or like some FPGA, which is not error prone. But here these are error prone and they'll introduce extra errors. Uh, so even if these LDPC quantum LDPC codes are low density, this low density also how low density kind of matters, and they need to be really good to suppress errors.
Thank you. So I have another question. So are you there, Asit?
Yes, sure.
Yeah. So like in terms of the future research, what are the kind of the open problems people are looking at now in this quantum error correction?
Okay, so there are many. So one is this code construction. I said here, right? So constructing codes which are like hardware amenable to the current hardware. So you kind of there is a need to co-design codes and the architecture simultaneously. Like by co-designing, I meant so if you look at these standard graphs, here I'm taking each variable node can be connected to each check node, right? So but in the hardware, there are this constraints that you arrange these variable nodes in a two-dimensional grids, and the variable node can be involved in a check node if it is like uh, uh, if it is next to it. Um, so basically, these are qubits, and each check node will have also ancilla qubits. So you take this all these qubits and arranged them in a two-dimensional grid. So a check node can be involved with variable nodes only if they are neighbors geometrically, and this kind of doesn't allow to optimize the codes the way you want to do, or generally they used to be done in classical LDPC literature. So this is one problem. uh, uh, Designing codes. Then the other issue is, like, as Narayanan is going to talk next, so this is only memory, right? So you still need to do manipulate. So now we are like storing information in just storing information. Like, we are thinking this code as a memory and storing information, but you should be able to manipulate this information. Not only that, you should be able to do you know, a set of gates that are like universal in a fault tolerant way. So that is very, very challenging. I mean, we are just scratching the surface. No one even knows how to do it without using like different families of codes, because one code would particularly support like only one kind of operation. Basically, mm, there are these universal gates in classical digital circuit design, right? Similarly, quantum also has a set of universal gates, and then you need to do them fault tolerantly. So now you are having your logical qubits in these codes, but you should have logical operators to do those each of those universal each of the gates in the this universal set of gates fault tolerantly. That is very, very challenging. Then the other problem is decoding itself. So I kind of like defined this decoding problem in a superficial way. So we have kind of solved this problem only partially. There are other problems in decoding itself. For example, as I was saying you, that this C naught gates in the syndrome extraction, I assumed them to be perfect, but in practice they're never perfect, and they'll introduce errors. In fact, they'll introduce errors, and um, when you when you track them, the way I was tracking this X is kind of getting propagated to the ancilla. This is desired. But in some cases, if there is an error, for example, instead of this Q1, if there is error in the ancilla here, it will upward propagate to the data qubits, and that is kind of dangerous. One fault can lead to many errors in the data qubits. Then how do you handle such errors? There are ways to handle such errors, but they're extremely complex. Now people have been thinking to do run them in this GPU where like people train their neural machine learning models. But it's kind of efficient, and as the code size would increase, this problem would become more and more prominent. Then as that would increase your decoding time. More decoding time is more error. It's kind of, yeah, I mean there are many problems. And then like there is this problem called compilation problem, right? Like how do you um, uh, design, let's say you want to do some quantum simulation, then how do you compile, uh, you know, the circuit on physical qubits, right? But you have to now operate on this codes which has logical qubits. So how your physical circuit would translate to logical qubits? Then there are optimization around there. How do you minimize depth? That is basically how fast you can execute the logical circuit, or like how do you uh, yeah, basically how fast you can execute your logical circuit. And like how do you minimize the number of gates in your logical circuit, because these gates are also faulty.
Okay, thank you. So there's a question in the chat box. I'll just read it. Could you refer any simulation tool that supports qubit communication? That is the question.
uh, I don't know of any. So by qubit communication, you mean can you elaborate a little bit? Like
Anand Lakshmi, can you elaborate in the chat box what you mean?
so there are toolboxes for this error correction part. I'm aware of that. Uh, uh,
So now, are there toolboxes in MATLAB for quantum communication?
no. So
Okay.
there are this uh, toolboxes in there are this GitHub repository which are written in Python for quantum, this QLDPC decoders, but not in
I
MATLAB.
think her question is, she says channel. I think she's asking about modeling the quantum channel or something like that using simulation tool.
Okay, I'm not aware of any simulation tool which models channel, but these are like, so you take the mathematical model and then you just implement it in any language you prefer, right? Like, so this typically this like people consider this depolarizing channel, which is like kind of equivalent to binary symmetric channel, where there are these bits which gets flipped with certain probability. That's all, and that probability is the your parameter. For example, the curve I had. So the BAC parameter is kind of like depolarizing probability. Then you simulate it. Um, so this mapping from this stabilizer code to the classical code with which satisfies certain condition makes the simulation easier, right? So the CSS code is like kind of, if you have n qubits, your your vector space is kind of not kind of, it grows exponentially with number of qubit, as you can see here. But once you map it to binary, it's a very powerful mechanism mapping this to binary. It reduces the vector space to just n. For n qubits, you need a vector space, uh, like the vectors are like what you need to, the code you need to simulate would have block length just this little n, not 2 raised to n. So you take so basically, if if we had not known uh, this this mapping from group to this binary mapping, then it would be just impossible to simulate any of this. Because of that mapping, uh, mapping these polymatrices to these binary vectors, we are able to do a classical simulation of these codes and evaluate their performance. Without that, it won't be possible.
Thank you. So just another question. So, like we have source coding in classical communication, and we are trying to do this joint source channel encoding. So, is a similar thing in the quantum field also? Any source coding or joint source channel coding?
I know of source coding. You'll find that in Nielsen and Chuang, or even the other quantum information theory book by um, forgetting. Source coding is there, but I don't know about uh, joint source and channel coding.
Okay, thank you.
Yeah, the book, you'll find this in Mark Wilde's quantum information theory book.
So the GitHub repository link has been posted in the chat box. You can have a look at it. So Asit, there's a question in the chat box that the GitHub link is showing 404 error. Is it working? That is a question in the chat box.
I sent it again. You can try.
Asit, your Zoom chat is visible. Maybe you can stop sharing the screen. Dr. Asit for the presentation. Now I will share the feedback link with you in the chat box. You can give the feedback. The attendance link will be shared at the end of the next session. We'll again meet at 8 p.m. Okay. Next session will be at 8 p.m. by Dr. Narayanan Rangaswamy, Assistant Professor at University of Arizona. That will also be on quantum error correction. I have posted a link for the recorded videos also. I shared it in the afternoon in the WhatsApp group. I have posted it here also. Okay. Thank you. Let's meet at 8 p.m. Dr. Narayanan. I will make you a presenter. Yeah, I have made you a presenter. We will just introduce you shortly now before you proceed with the talk. Hari Ganesh, can you please introduce the chief guest?
Yes, yes, sir. Good evening, everyone. I would take immense pleasure in welcoming Dr. Narayanan Rangasamy, who is a tenure track assistant professor of electrical and computer engineering at the University of Arizona. He also works at NSF Engineering Research Center for Quantum Networks in the university. From September 2020 to August 2022, he was a postdoctoral research associate with Bain Basic in the Department of Electrical and Computer Engineering at the University of Arizona. He completed his PhD in Electrical and Computer Engineering at Duke University in May 2020 under the supervision of Henry Pfister and Robert Calderbank, and continued there as a research associate until September 2020. His dissertation was centered on error correction techniques for fault-tolerant quantum computing and quantum communications. Earlier, he obtained his MS in electrical engineering from Texas A&M University in December 2015, where he was advised by Henry Pfister and Krishna Narayanan for his thesis on polar codes. During the summer of 2015, he was a graduate research intern at Alcatel Lucent Bell Labs, Stuttgart, Germany, where he worked on the spatially coupled low-density parity check codes with Laurent Schalman and Wahid Arif. He received his BTech in Electronics and Communication Engineering from Amrita University, Coimbatore, India in June 2013. His current research interests are classical and quantum error correction, quantum computing, quantum networking, and quantum communication. He is a reviewer for several journals and conferences. He served on Posters Program Committee of 2022, the International Conference on Quantum Computing and Engineering. He is a member of IEEE. With this brief introduction, I would now like to hand over the session to Dr. Narayanan Rangasamy. Please, sir.
Thank you so much, Hari Ganesh, and thank you so much, Dr. Sudarshan, for inviting me to give this talk. Can you confirm that you can hear me okay?
Yes, sir. We are able to hear you, sir.
Okay, thank you so much. Let me start by sharing my screen. Okay, can you see my screen?
The screen is visible.
Okay, thank you so much. Okay, so this talk is, I think you just heard from Dr. Asit about some quantum error correction and LDPC codes. So there might be a little bit of overlap between the talks, but I will also tell you more about what is fault tolerance and how do we construct fault tolerant operations in quantum computing. So this talk broadly is going to be an introduction to fault tolerant quantum computing. And feel free to stop me in the middle if you have any questions. I'm happy to take them in between. You don't have to wait till the end. Okay. So the outline of this talk is, I don't know the backgrounds of everyone here. So I will quickly review classical error correction using binary error correction codes. And after that, we will transition into the basics of quantum computing, quantum mechanics, just a little bit that we need to understand the remaining of the talk. Then I will go into quantum error correction, and we'll talk about constructions and so on. Then we will connect quantum error correction to classical error correction and see take advantage of this huge literature that we have over the past 60, 70 years in classical error correction. That will lead us into all the exciting codes that we have today. Then in the next part, we'll talk about fault-tolerant gates, which are fault-tolerant operations that you perform on the information you encoded into the code. And so we'll look at a few examples, and I'll tell you a little bit of my own work there. And finally, in the last few slides, I'll talk about state of the art and how people are thinking these quantum computers. So that's going to be the structure. So let me get started with a quick review of classical error correction, and let's start kind of big picture. So we use it in many different systems, But if we take digital communications as an example, I think many of us will know that when you talk over the phone, you have an A to D converter that converts your analog sound waves into digital electrical signals, and then you add redundancy to your message using an error correction encoder. Then you modulate into waveforms that you send over the channel, where you pick up noise, distortion, and so on. The channel at the binary level, the channel does something to the bits that you transmit. Then you demodulate, and then you error correct, and then you have a D2A converter, which goes to the destination. So this is how communication systems, and you can kind of redo this for hard disk and data storage as well, and many other applications. So the key point here is that we have a model for the channel. We at the level of bits. Of course, you can talk about the model of the channel at a more physical layer level, but for this talk, we'll be interested at the level of bits. So you have some channel model that says how input bits are transformed into output bits. And this is typically characterized using a transition probability matrix, which tells you that if you send bits xi and you get output yi, what's the probability that bit xi became bit yi? And a memory-less assumption that we commonly make is that we have every bit is independently acted upon by the channel. That's given by this joint probability distribution becoming a product of individual probability distribution for every bit. So a classic example that's very useful to study is the binary symmetric channel, where you have a channel model where you have input bits and output bits. And so the bits get flipped with probability p symmetrically for both 0 and 1. And with probability 1 minus p, they're not flipped. And so for this channel, what will happen is if you send bits through in, some bits get flipped. You don't exactly know which bits got flipped. So if you send only your raw message at the receiver, there's no way of knowing that this 1 is incorrect and needs to be corrected to 0. This is why we encode using an error correcting code, which adds redundancy. So here is a simple example where you're just repeating every bit 3 times. That's the redundancy. You're adding 2 bits of redundancy for every message bit. And in this case, if you transmit 3 bits and the channel still flips only 1 bit, then of course, these 3 zeros, this string is closest to all zeros instead of all ones, because it's only 1 bit away from all zeros, whereas it's 2 bits away from all ones. So you say that under this memory-less assumption of the channel, this is more likely to have been 0, 0, 0, which you decode back to the message 0. That's kind of how error correction. So formally, we say that a code C is defined as the null space. It's the binary null space of a parity check matrix H. So which means that if you think of the code words, which are binary strings of length n, then as a row vector, then if you do HC transpose, you should get all 0, which means that every row of H, the code word must be orthogonal to every row of H in the binary field. So the example that we saw in the previous slide is the repetition code, where you only have 2 code words. So for message 0, you encode into 0, 0, 0. For message 1, you encode into 1, 1, 1. And the parity check matrix in this case is to just check that adjacent bits are the same. So this one says, for example, if you do HC transpose, so for the code word 111, if you take the inner product of the first row in this column, it basically says that 1 times 1 plus 1 times 1 is supposed to be 0, mod 2, which just means that the first 2 bits have to be equal. Similarly, this says the second and third bit have to be equal. So combined together, this means that all 3 bits have to be the same, and the only strings that satisfy that are these 2. So every row of H gives you a simple parity check, and that's how we define a code using. So if H has dimensions n minus k by n, then C is a binary subspace of dimension k. So we say that the code is N, K, and D, where K is the number of message bits you encode into N code bits, and N is typically larger than K. And D is called the minimum distance of the code, which is defined to be, for a linear code like this, it's defined to be the minimum number of ones in any code word. So for example, in this code, if you take any non-zero code word, the minimum number of ones is 3, because there's only one. And so this code will have distance 3. So this is said to be a 313 code. It encodes 1 bit into 3 bits, and any non-zero code word has at least 3 ones. The other way to see this, if you think a little bit about this calculation that we did here, is this is also the same as defining it as the minimum number of linearly dependent columns of H. So here you can see that every 2 columns of H will not be linearly dependent, but all 3 columns are linearly dependent, because if you add all 3, which is exactly what this multiplication is doing, then you get 0, 1, 2. So this is how we define a classical code using the parity check matrix and define its parameters. Now we will look at a specific perspective of codes using these syndromes. So let's say you consider this binary symmetry channel and you transmit this code word through the channel. And what you receive is actually this code word binary sum with some error vector E. So E is the same length as C. And wherever E has ones, it means those bits are being flipped by the channel. And so every entry of E will be picked from this distribution here. So the syndrome is defined to be the product H times Y transpose, where Y is what you receive. And if you expand Y, and by linearity, if you take HC transpose plus HE transpose, then because a code word always satisfies, it's in the null space of the parity check matrix by definition. So HC transpose is 0, and you're left with just HE transpose. So every error will have a syndrome, and you can compute this and use the syndrome to decode what the error is. So for the repetition code, we had this parity check matrix. So for all single bit flips, you can compute the syndrome, and you will exhaust all possible syndromes. So because with only 2 rows of H, the only possible syndromes you can get are 2 bits, which is 0, 0, 0, 1, 1, 1, and 1, 0. And these are mapped to these canonical error vectors with a single bit being 1. And these are the errors that you can actually correct. So if you had an error that is 0, 1, 1 with 2 ones, then you cannot correct it because this code is not capable of correcting it. So error correction proceeds by computing the syndrome for the received vector, and then looking up this table. For example, for you will compute the syndrome using this calculation, and then you will just look up this table to see which error that corresponds to, and then declare that as the error that happened, and then you can add the error back to Y. If you do Y plus E, then you get back C. But of course, if you have more than one error, you will pick a wrong error vector, because, for example, if you do 0, 1, 1, 0, 1, 1 will have the same syndrome as 1, 0, 0. You can double check that, because if you add these two, then the sum of these two will be 1, 0, and that's exactly the syndrome. So if the channel actually flipped the second and third bits, you will actually declare that 1, 0, 0 was the error. So the actual error, which is 0, 1, 1, plus the error that you declare, will actually result in 1, 1, 1, which is actually a code word, which would be a wrong decoding. So this is how kind of syndrome-based error correction works. And once we understand this, we can actually see that D, which we previously defined as the minimum number of linearly dependent columns, is actually the minimum number of bit flips for an undetectable error. In this case, an undetectable error will be a code word, and we only have 2 code words in this case. So it's 1, 1, 1. So if you take 1, 1, 1, that's an undetectable error because it's a code word. So if the actual error was itself some code word, then this syndrome will always be 0, and you will declare it to be 0. and that would be an undetectable error. So, so this is the perspective that will be useful later for us when we get into quantum computing, that the minimum number of D is just the minimum number of flips in an undetectable error. Any questions so far?
Fine so far.
Okay. And quickly, so let's recall, I think this is what you might have seen in Dr. Asid's talk. So you can decode classical codes on these Tanner graphs. So Tanner graphs are bipartite graphs where you have circles representing bits and squares representing parity checks. And so for example, for this code, which is a little bit larger than the 3-bit code we looked at, so here are 2 parity checks, and these correspond to these parity check equations. And so this graph basically encodes these checks. So C1 is attached to X1, X2, X3, which means that the sum of those 3 bits is supposed to be 0, and similarly for C2. So this is what the graph structure enforces. And these WIs are basically the probability of flips that we directly get from the channel transition matrix. Now, how we decode on these graphs is you can do kind of bitwise decoding. So let's say we want to figure out what the actual value of the first bit was, depending on what we receive as y. So if you frame this as a problem, then you're trying to find the argmax of the marginal distribution of x1 given the received vector y. And of course, you can replace this marginal distribution, but by the full marginalization of the joint probability distribution. And then using Bayes' rule, you can change this into y given x times x. Of course, there is a denominator, but that wouldn't depend on these variables because it sums over everything. So we believe that it doesn't change the argmax. And once you get here, then you can substitute what we know about the channel. So if you assume the channel is memoryless, then this transition probability is just a product of the individual transition probabilities. And the probability of x it's basically 1 if it's a code word, and it's 0 if it's not. And so the way you enforce it is using these indicator functions, so this indicator function would be 1 if the parity check C1 is 0. And similarly for the second indicator function. And then you can group these terms by the variables that they involve. And you see, and you basically use the distributivity of addition over multiplication. And using that, you can actually group these terms. So what you actually do on the graph is you initialize all the variables using the channel values. And after that, you can perform this computation and highlighted in blue on this part of the graph. And simultaneously, you can actually do the computation in orange on this part of the graph. So this is where the speed comes from. And then you send the resulting sums as messages to this bit. And this bit basically takes the product of the channel value times the incoming messages. And then you take the argmax of that. So this works perfectly and very well for a tree. When you have loops, it's more complicated, but this is how iterative decoding works on Tanner graphs. And the famous codes that use these kind of decoding algorithms are these low density parity check codes, which are defined by sparse Tanner graphs, where the number of edges will be small total number of edges that are possible. So in this case, for example, every variable is connected to 3 checks, and every check is connected to 5 variables. So and so you can define classes of these codes, and there's a lot of literature on this. And this would be the parity check matrix corresponding to a graph like this. Okay, so that kind of completes the review of classical error correction. And so we'll see how some of this needs to be adapted when you do quantum error correction and what things become different. Are we doing okay? Can we proceed? Okay, if I don't see any questions, I'll keep
Yeah, we are
proceeding.
doing fine. Yeah.
Okay, so let's start with some basics of quantum. So the main kind of change that we have is that instead of dealing with bits, we are going to deal with qubits or quantum bits. So bits are binary strings that we all know very well. Qubits are basically vectors in a complex vector space. So for one qubit, there are two basis vectors. So this is a complex vector space of length 2. So you have two basis vectors, 1, 0, 1, 0, 1, and that's what we represent by this symbol. And this is to be read as ket0, K-E-T, and this is ket1. Now, so that's how you define the basis states for a single qubit. And of course, you can take linear combinations, which we will see shortly. Now, what can you do with a single qubit? So these are the basic operations called Pauli operations. So Pauli operators are x, z, and y, and also the identity. So the identity does nothing. If you take x, it's actually the bit flip. So it basically flips the binary value inside the ket. So this is kind of like a classical NOT gate. The phase flip is kind of purely quantum, where it fixes the ket0 state, but for the ket1 state, it picks up a phase -1. And the bit phase flip y is a combination of x and z. And you also add this imaginary number I. So it flips 0 to 1, 1 to 0, but also picks up an extra I in both cases. So you're doing both z and x, and then also a y and I. And the reason this I exists is to make this matrix representation of this y to be Hermitian. So these Pauli operators are unitary matrices, but they're also Hermitian matrices, these ones. So these are kind of the basic operations you can do on a qubit. We can also think of these operations as errors. So the quantum version of a symmetric channel, we already saw the binary symmetric channel. The quantum version is defined as follows. So if you take an arbitrary qubit state as input, which is a linear combination of these two basis states, such that it is normalized, then if you send an arbitrary qubit into this channel, which is typically called a depolarizing channel, then, and if the channel parameter is epsilon, in the binary symmetric channel, we use P, here I'm using epsilon. Then with probability 1 minus epsilon, nothing happens to the state, but with probability epsilon over 3, it can apply x, z, or y. So this is kind of the standard channel that we look at in a quantum case. And it's also information theoretically kind of important because this is the kind of channel where you have very little information about what happened because there is no bias, there is no kind of interesting property. It's just this property. So that's for a single qubit. Now, what happens when you have multiple qubits? Then these basis states now are over kind of longer complex vector spaces. So for every qubit you add, you have to add a power of 2. So with 3 qubits, these states will be of length 2 to the 3, which is length 8. Now the Pauli operators in that case will be tensor products of the Pauli operators on individual qubits. So we represent it using this tensor product, which is also the same as the Kronecker product. Typically in notation, we put subscripts to kind of remove this tensor product. So if you put subscripts 1, 2, and 3, that denotes the qubit on which that Pauli operator is acting. And sometimes we even drop the subscripts and just write a string like this. It's assumed that X is acting on the first qubit, Z on second, Y on third. So tensor product is
here. Just a doubt.
Yeah.
So the depolarizing channel, you have all the 4 Pauli matrices, right? I, X, Z, Y. Like, can you have just one of them also, like X alone without Z and Y? Is that also possible?
So sometimes in special cases, we also look at bit flip channel alone or phase flip channel alone. Or sometimes you can have independent X and Z. So in this case, this Y, like I said, is a combination of X and Z. So Y is kind of a correlated error between X and Z. But sometimes it's also valid to look at independent X and Z channels. So there are different variations of this also, yeah.
Okay, thank you.
Okay, so when you have more than one qubit, you do this tensor product. And so the Pauli group, formally as a mathematical group, is defined as the tensor product of all these Paulis, along with a global phase that can be one of these 4. These are basically 4th roots of identity. And so that's the group, and all of these are Hermitian. And these, if you count, you'll have, it's not showing with the, so just to be clear about the question, so it's not mandatory. So sometimes channels can be biased. Sometimes they will, apply Z with more probability than X. So these are called biased noise channels. This really depends on the hardware. And so we take the advice of experimentalists to determine what these probabilities should be. But as theorists, if we don't want to specialize for any particular channel, the kind of worst case assumption you can make is the depolarizing channel because it has a high entropy. Does that answer the question?
Thank you.
Okay. Great. Yeah, so all these Hermitian operators, if you count, like on each qubit, there is 4 Hermitian ones. And for n qubits, there will be 4 to the n. And these you can actually prove or form an orthogonal basis for all 2 to the n by 2 to the n matrices. And they form a basis under this inner product called the Hilbert-Schmidt inner product or the phase inner product. And so this is a super important property of the Pauli matrices. This is why we tend to think of everything in quantum computing in the Pauli basis because it's very useful. So because of this result, we get a very important insight. Quantum noise channel. So I showed you the example of a depolarizing channel, but a general representation of a noise channel is using this so-called Kraus representation, Kraus, where you say if you take an input state psi, and this is to be read as an outer product. So think of ket psi as a column vector, and this is called bra psi, which is a row vector with a complex. So this is basically a Hermitian conjugate of this vector. So this is an outer product. So this is a column and this is a row. So this is a matrix that you're inputting here. And EIs are basically matrices that represent kind of noise operators or Kraus operators. And the only condition they need to satisfy is this so-called completeness condition, that the sum of EI dagger EI, where dagger represents the Hermitian conjugate, you get the identity. So for the depolarizing channel, for example, EIs will be I, X, Y, and Z. So this is the general representation of a noise channel. And a very, very important result, which Dr. Asit might have also told you in his talk, is this discretization of errors. So think of quantum computing, right? It's happening in kind of complex vector space, and all these errors can be kind of continuous. But the reason we kind of tend to think of them as Pauli errors is because of this principle, which says that if a quantum error correcting code that you can construct can correct errors, some set of errors EI that you pick, then actually the same recovery operation that you use to correct these errors can also be shown to correct errors that are linear combinations of these EIs, right? So for example, if you can correct all Pauli errors on a single qubit, so I, X, Y, Z, and we know that IXYZ forms a basis for any matrix on one qubit, which means this result says that you can actually correct errors that are linear combinations of IXYZ, which is everything. This is why we say that if you have a single error correcting code, then by this discretization principle, as long as you show that every single Pauli error can be corrected on one qubit, then you can actually correct arbitrary errors on one qubit. So this is why we only consider Pauli errors. There are some kind of technicalities and caveats, which I'm not talking about today, but this is kind of the underlying principle that this linear combination is a pretty important insight. So this is actually why quantum computing and quantum error correction even works. If you think of analog computing, if you have errors that are totally analog and they kind of rotate the space, then it's very hard to exactly detect what real value they rotated by and then kind of invert that rotation. But we don't have to deal with that in quantum computing because we can always measure and discretize errors and then use this principle to correct them. Okay, so we've looked at the Pauli operators. Now let's look at some a key property of these Pauli operators, which is commutativity and anti-commutativity. So I'm using kind of circuit notation here. So think of this as a circuit where a qubit starts in the left, and then here time in circuits goes from left to right. So I'm starting with a qubit state here, and first you apply X, then you apply Z, and this is the output state. When you write it as a matrix acting on the state, you have to take time to go from right to left, because here is the state, and you first apply X like here, and then you apply Z here. So just hopefully this direction is clear. So the key thing to note here is that any two poly operators which are non-identity anti-commute, which means if you reverse the order of the operation, then you pick up an extra negative sign. So Zx is minus Xz, Yx is minus Xy, Zy is minus Yz. So this is the key property. So of course, on a single qubit, any two poly matrices anti-commute, not identity ones. But when you go to more qubits, they can commute. So to see that, recall that this is a key property of the tensor product. So if you have A tensor B times C tensor D, then you can actually multiply the corresponding components and then write it as AC tensor BD. So if you apply this here, so for example, I have two qubits, and I'm applying X followed by Z, X followed by Z. So in kind of this notation, I'm applying first X tensor X, and then I'm doing Z tensor Z. So here is X tensor X followed by Z tensor Z. Now, if I use this property, then I can multiply Z and X and Z and X. So I get this, but ZX is minus XZ. And then these minus signs are just scalars, so they just multiply and cancel out. And I can again separate this in this form and write it as X tensor X times Z tensor Z, where I've changed the orders of the two operators, but I don't have any overall sign, which means they actually commute. And in circuit notation, this means that this is the same as changing the order and putting the negative signs using this, and then these negative signs cancel, and I get that they actually commute. And once poly matrices commute, you can do some very interesting things, which forms the basis for quantum error correction. So we can first define a group called a stabilizer group, which is just a set of commuting poly matrices. So here, when I write this angle bracket, that means whatever I'm writing in here with the commas are the generators of the group, and the actual group will be all possible products of these generators. So here I have XX and ZZ, and so if I multiply, you can double check that I will actually get minus YY. And of course, if you multiply XX with itself or ZZ with itself, you get identity. So if you expand this group, you actually have 4 elements in the group, but the generators are XX and ZZ, and they commute. And the key result from linear algebra is that whenever Hermitian matrices commute, they can be simultaneously diagonalized. So recall the eigendecomposition or diagonalization in linear algebra. When you have Hermitian matrices that commute, they actually have a common basis of eigenvectors, which means you can diagonalize both of these matrices with respect to the same basis. And this is the key. The other thing I want to highlight is that we already said that these poly operators are both unitary and Hermitian. And because of that, the only eigenvalues they can have is +1 or -1, which is something you can verify. So this says that when you have commuting operators, they can be simultaneously diagonalized. They have a common basis. And so the only eigenvalues they'll have is +or -1, and they will have a common set of eigenvectors. So for this specific group, this common eigenbasis is famous, and it's called the Bell basis or the EPR basis for Einstein, Podolsky, and Rosen. So the Bell states, there are 4 of them. So this is how they are typically denoted: P plus, V minus, psi plus, psi minus. And when I write a binary string inside the ket, I'm actually kind of using shorthand notation. This is actually shorthand for ket0 tensor ket0 plus ket1 tensor ket1. So this will be a column vector of length 4, 2 to the 2, because there are 2 qubits involved. And you have these 4 states, and you can actually verify that these are actually eigenvectors of both of these operators. So for example, again, using the same tensor product property, if you apply x tensor x to phi plus, because of this tensor product property, you can apply x to individual qubits in both terms of the superposition. And you see that x0, we know that x is a bit flip, so it kind of changes 0 to 1 and 1 to 0. But this is just the same state that you began with. And so this is just phi plus, which means you have an eigenvalue of +1. So xx acting on phi plus is just phi plus, which means this is an eigenvector with eigenvalue +1. And similarly, if you apply zz to this state, you will also get eigenvalue +1. But for other states, you will get different combinations of +1 and -1 for xx and zz. And so you can have only 4 combinations. So this one will be 1, 1, this will be 1, -1, this will be -1, 1, this will be -1, -1. Now, once you define a stabilizer group, we can now define a stabilizer code, which is basically the subspace that is spanned by all the eigenvectors of S with eigenvalue +1. That's how we kind of canonically define it. In this case, that means that it will be only the state phi plus. So this is a stabilizer group, and all of these are eigenvectors, but the only subspace that has only +1 eigenvalues with both of them is the one-dimensional space that is generated by this single vector phi plus. So in this case, you don't get anything much interesting. It's just a single state. It's not really a subspace. It's one-dimensional. It's a single state. But this is the idea. So I want to kind of emphasize the idea here because we'll be using this for other codes. The first step to define a code is to define a stabilizer group, which is defined by a set of commuting Hermitian polymatrices. And the group is generated by those matrices. And then you use linear algebra, you simultaneously diagonalize them. You find the common set of eigenvectors. And then from the common set, you see which eigenvectors have +1 eigenvalue with all of the operators. And you define the code to be the linear combination of those +1 eigenvectors, or basically the subspace spanned by those +1 eigenvectors. So let me pause here. This is kind of the key idea for quantum codes. So any questions on the definition?
It's fine.
Okay. Good. Now let's proceed. So now we have defined what a code is. We have mathematically looked at this. Let's see what actually happens in the lab using an example. So now I'm going to define n and k for a quantum code. So we already saw in the classical case how k bits get encoded into n bits. In this case, now I'm taking an example where k is 1 qubit, and instead of a message bit, we in quantum error correction, we typically call this a logical qubit. So this is the kind of qubits on which you define quantum algorithms. Say like you want to factor integers or do some other interesting algorithm. These are defined on logical qubits. So here in this example, in this toy example, I have 1 logical qubit, which means the state is a general single qubit state. And then these 2 qubits, which start in the 0 state, are called ancillary qubits. These are basically kind of scratch qubits or helper qubits. Now this operation, so this is an encoding circuit for this code. And so this operation is called a controlled NOT gate. So it's controlled by the first qubit and it NOTs the second qubit. So it applies X to the second qubit only on some condition. So the first qubit is 0, it doesn't do anything to the second qubit. If the first qubit is 1, it flips the second qubit. So if you apply this in superposition, because this qubit starts in 0, so for 0, 0, nothing happens, but the 1, 0 will become 1, 1. So in here, the state that you will actually have is between the 2 qubits is ket 0, 0, ket 1, 1, of course, with the same alpha beta. And again, if you apply the same rule to this control NOT gate, you end up getting this state. So this control NOT can be thought of as a reversible XOR because it retains the first input, but the second output is basically the XOR of the second input with the first input. So think of this as a reversible XOR gate applied in superposition to individual terms. Okay, so once you have encoded the single logical qubit, you end up with 3 physical qubits, and an arbitrary encoded state looks like this, where alpha and beta is the actual information in the logical qubit, and these are the kind of like carriers. So think of this as like modulation. If you want to make an analogy to classical communication, think of these as modulation. So this was a different modulation, this is a different modulation, except that this comes with some error correction. Okay, so I've defined how to take a logical qubit and encode using a circuit, but is this a stabilizer code like we defined in the previous slide? It definitely is. But in this case, the stabilizers turn out to be these two Pauli operators, Z1, Z2, and Z2, Z3. You can verify for yourself that applying the rules for Z, remember Z acting on 0 is 0, Z acting on 1 is -1. So using those rules, if you apply Z1, Z2 to this state or Z2, Z3 to this state, you will always get back the state unchanged, which means the state is a +1 eigenvector of both S1 and S2. And crucially, this eigenvalue being +1 for both stabilizers is independent of alpha and beta. So whatever information you had in the logical qubit, after it is encoded, it is always an eigenvector of S1, S2. So it does not depend on the data. And that's very, very important, because when we do error correction, we don't want to disturb the data. We don't want to disturb alpha, beta. We only want to know if some bits got flipped here. Okay, so that's the definition of an encoding circuit. That's the definition of a logical and physical qubits, and the stabilizers for this particular code. Now let's see what happens when you have an error. So let's say you prepared this encoded state, and then the channel applied a bit flip to the first qubit. Now, classically, remember we computed syndromes. So you had a code word being transmitted, and you added an error vector, E, and you had C plus E being Y that you actually received. And then you computed the syndrome as H times Y transpose. In the quantum case, it's complicated. So you have this encoded state, but you cannot see it. There is no kind of received vector like Y. You cannot see it, and you cannot just directly compute this in a product XY transpose. So you have to actually build a circuit which computes the syndrome for you. And in this case, the circuit is this. So we know that Z1, Z2 is basically checking the phase parity of the first 2 qubits, and Z2, Z3 checks the phase parity of the second and third qubits. And so to actually measure that, it turns out that you can actually do 2 CNOT gates between the data qubits and a scratch qubit or an ancilla qubit. And after you do that, you measure the ancilla qubit. And when I'm measuring a Z, which means that I can get only 2 eigenvalues, +1 or -1, because Z is Hermitian and unitary. And if it is +1 on both sides, so this is for S1, this is for S2. So if I get +1 on both sides, it means my syndrome is ideal. It's both +1, so I assume that nothing wrong happened. But if any one of them is -1, then I say that something wrong has happened, and then I run a decoder to figure out what happened. So in this case, we have an error X here. You can actually kind of rewrite this circuit by pushing the error forward. And you can see that because this is a reversible XOR, where if this bit gets flipped, then this output is an XOR of this qubit and this qubit. So naturally, if this is flipped, this will also be flipped. And so that flip will propagate, and it will flip the measurement result from +1 to -1. And that's how you detect that some error happened, and then you run a decoder to figure out what happened. So in the lab, this is what we do. You construct codes, you prepare these encoded states, and regularly you perform these syndrome measurement circuits, and then you look at the syndrome, and if it's non-trivial, then you run a decoder. Okay, good. So that's about error correction. Now let's also look at how to do computation, because then we'll combine these two and look at fault-tolerant quantum computing. So when you do computation, you have two types of gates, Clifford gates and non-Clifford gates. The way Clifford gates are defined is these are unitary operations that conjugate a poly to another poly. So conjugation means you're sandwiching a poly operator E by U and U dagger. And if you always get the output to be a poly, then you say that U is Clifford. So as an example, here are some gates. So P is called the phase gate. In textbooks and in some papers, you will see this as denoted as S. To distinguish S from stabilizers, I'm using P for this talk. So it turns out that P is the phase gate, which is actually the square root of the Z. And it turns out that it commutes with Z. So P and Z, you can change the order, nothing happens, which means P, Z, P dagger is Z. But PX, P dagger is Y. So instead of doing the dagger, I've just moved this to the other side and removed the dagger. So it's all equivalent. So this is the phase gate, and the Hadamard is another type of gate, which turns Z into X and X into Z. And this control NOT that we looked at, for example, will change X to XX. And this is the property we used in the previous slide. So if you rewrite this C0 and this X, you can push this forward and write this as C0 followed by XX. But Z on the control qubit of a C0 does not propagate down. It stays only in the control qubit. So there are like kind of conjugation relations like this, which we use all the time. And this is the signature of Clifford gates. A non-Clifford gate is one where at least one poly operator will be conjugated to a non-poly operator. Okay? So an example of that is this T gate. So the T gate is actually the square root of P, or in other words, P is the square of T. If you apply T 2 times, you get P. So T turns out to be a non-Clifford gate. So if you conjugate X by T, you do TX T dagger, you don't get back a poly operator. So it turns out that for universal quantum computation, if you want to do arbitrary quantum circuits that is permitted by quantum mechanics, then you have to do 3 types of gates, H, T, and C0. So think of these as the quantum analogs for the NAND gate and NOR gate, which we know is universal for classical computing. So if you can do these 3 gates arbitrarily well to arbitrary precision and accuracy in the lab, then you have a universal quantum computer. So for a single qubit, an arbitrary circuit will just looks like a sequence of H and T, and it turns out that using this arbitrary sequences of this, you can perform any unitary on one qubit. When you have more than one qubit, you will also have C0s appear every now and then. Okay, so these are still logical circuits acting on these logical qubits when no errors happen. But of course, in reality, these logical gates are not ideal. If you directly do them in the lab, these gates will be noisy because the hardware is noisy. So all these gates, when you apply, there will be noise that comes with it, which means the output state might not be the one that you want. It might have been affected by noise. So this is why we encode logical qubits into physical qubits. And then you do all gates, hopefully in a fault-tolerant manner, and then you decode. And if you corrected all the errors, then after decoding, you will end up in the state that you actually want. But to accomplish this, you have to actually translate or synthesize logical gates into physical gates that are also fault-tolerant. So there are 2 kind of goals in quantum error correction and fault-tolerant quantum computing. One is translating these logical gates to fault-tolerant physical gates, and the other is to, of course, do error correction itself on the encoded state. So that's kind of the main goal of error correction. And like I said, H and C0 are Clifford gates. T is non-Clifford, and we'll see how this affects computation later. Okay, good. So any questions so far? Okay, if not, I'll proceed, and feel free to stop me if something comes to mind. Okay, so to do this logical operation business, like I showed you here, let's look at our toy example and see what logical operators actually mean. So after you have encoded this logical qubit into 3 physical qubits, let's say you want to actually apply an X gate on the logical qubit. Of course, you have now encoded it. You don't have access to this logical qubit anymore. The only thing you have access to in the lab are these 3 physical qubits. So any manipulation is supposed to be done only of these qubits, and you have to do it in such a way that it affects the encoded information in the way you want. So for example, if you had applied a logical X, you know that it will flip 0 and 1. So you have to find a physical operation that has the same action. And it turns out in this case that if you flip all the 3 physical qubits, then you flip 111 to 000 and 000 to 111, which we of course know if we decode will go back to alpha 1 plus beta 0. So the right thing to do in this case is to apply X on all the physical qubits. And so we write this logical X operator to be XXX. Similarly, if you wanted to do a Z flip, we know that it will pick up a -1 for the state 1. And so on the physical space, if you apply Z to any of the 3 physical qubits, you will have the same effect. You will pick up a -1 because that Z will act on this 1 to pick up a -1. And so all of these 3 operations are equivalent and they have the same action, and all of these are logical Z operators. So this is what we mean by synthesizing logical operators. Any logical gate that you want to do, you have to find the physical version of it, which we typically represent by a bar on the top. So we have done this for polys, but you have to do this for the Hadamard, for the T gate, for the C0 gate, to be able to do universal computation. So we have defined N and K for the code, and we have defined how to find logical poly operators. Now let's look at the third parameter for the code, which is minimum distance D. So we already saw that if you have an X error, it propagates down the C0 using this conjugation rules, and that flips the measurement and you can correct the error. But a Z, using this rule that I showed you earlier, the Z on the control qubit does not propagate down. So this Z will just propagate through only on this line. It will never come down, so it will never affect this measurement. And because of this, if you have a Z error on this code, it will go undetected. There is nothing you can do about it. You just don't even know that something wrong happened. And that's exactly how we define the minimum distance of the code. It's the minimum number of flips or minimum weight of a poly operator for which is an undetectable error. So recall this. Was that a question? Okay. So recall that in the classical case, we redefine minimum distance as the minimum weight of an undetectable error. And that's exactly the same definition we are using here. In this case, an undetectable error is exactly a logical operator because it changes the logical state from one code state to another code state. But of course, both code states are in the code space and they will have a trivial syndrome. So whenever a logical operator happens, it will never show up in the syndrome because it is changing things within the code space. You're not going outside the code space. So in this case, because a single Z is a logical operator, we saw in the previous slide, a single Z on any qubit is a logical operator. Therefore, the minimum distance of this code is just 1. So it cannot even correct all errors. The first code that was shown to actually be an error correcting code in the quantum case was Peter Shor's construction. So he realized that this bit flip code that we looked at with ZZI and IZZ being stabilizers, where we know that it can correct a single X error on the qubits, he realized that that code can be concatenated with the X version of the code, which is called the phase flip code. So what he did was the following. So you take an arbitrary single logical qubit, you first encode it into the phase flip code, which means you do the same encoding as the bit flip, but then do Hadamards, which changes the basis from Z to X. And so the stabilizers are XX, X1, X2, X2, X3 instead of Z1, Z2, Z2, Z3. And then you take in each of the individual qubits and re-encode them into 3 physical qubits using the bit flip code that we have looked at. And this concatenation ends up giving you 9 qubits for one logical qubit. But actually, it turns out that in this case, you can correct any single qubit poly error. So the distance is actually 3, which means the minimum weight of an undetectable error of a logical operator in this case will actually be 3. So another way to look at this is to kind of organize the qubits like this. So every row corresponds to a triple of qubits encoded in the bit flip code, but they represent one logical qubit of the phase flip code. So this is the concatenation structure, and we can study this and look at its properties. So I won't go too deep into this today, but this was the kind of first construction to combine and concatenate an X error correcting code and a Z error correcting code into one code that corrects any error on a single qubit. And using the discretization principle, we know that if you can correct a single poly error, you can correct arbitrary errors. That's the first. So this came out in like 1994 or 5, just after Peter Shor came up with this famous algorithm to factor integers. And so this really kicked off the field and showed that you can actually correct quantum errors, even though they seem to be very continuous. Okay, so now I'm going to connect this quantum error correction to classical, and then we'll look at fault tolerance and then wrap up. So I'll start going a little bit fast. I want to go slow in the initial part so that the basics are clear. Any questions?
Fine so far.
Okay, great. Okay, so now let's see. So we have defined quantum error correction, but there's a large literature of classical error correction, and we want to be really able to use it. So the way we correct quantum to classical is using this binary notation. So if we have a tensor product of Pauli operators, we represent them as a pair of binary vectors A and B. So where A denotes the X component and B denotes the Z component. So whenever you have an X, you put a 1 in A and a 0 in B. Similarly, for a Z, you put a 0 in A and 1 in B. And if you have a Y, it's a combination of X and Z, so you put a 1 in both places. So given a pair of binary vectors, you can uniquely define a Hermitian Pauli operator. And we know that Pauli operators commute or anti-commute. So for example, if you want to check whether these two commute, you can actually do that in the binary representation. So you take each operator, you write the binary representation, call the binary representation AB and CD. And the right thing to do turns out to be this symplectic inner product, where you take the inner product of A with D and B with C. So all you're doing is looking for overlaps between X and Z or Y and X and so on. So if you compare the X component of one and Z component of the other, you see how many anti-commuting locations you have. Similarly, you compare the Z component of the first one and the X component of the other. Again, you get a bunch of anti-commuting locations. And if you add them all modulo 2, you get 0 or 1. So you'll get 0 only if they commute, and you get 1 if they anti-commute. So it's a neat representation for Pauli operators, and this really forms the bridge to classical error correction. So here is how you would do the inner product and verify that these two operators actually commute. So the way we define quantum parity check matrices is you take stabilizers. So for example, we looked at Z1, Z2, Z2, Z3. If you write it in this AV form, A is always 0 because there is no X. And so you get only get B components, which is 1, 1, 0, 0, 1, 1 for the locations of Z's. And if you stack these binary vectors as rows, you get a quantum parity check matrix or a stabilizer matrix. And if you divide it into the X and Z component as HA and HB, the relation they need to satisfy to be commuting. Remember, for stabilizers, they have to be commuting, which means their pairwise symplectic inner product should be 0. And the right way to represent that is using this equation. So as long as you can construct a matrix HS that satisfies this, you have a valid quantum code. Now, how do you compute syndromes? So we already looked at the circuit to compute the syndrome, but when you're doing simulation on your computer, it's helpful to think about syndromes in a different way. So for example, let's say you have your encoded state and some error happens E. Let's say the error was X on the first qubit, like we already looked at as an example. Then if you compute if you look at the action of the stabilizer, Z1, Z2, acting on this, we know that poly operators commute or anti-commute, and these two necessarily anti-commute because this X overlaps with this Z. So you pick up a -1 and change the order. But now ZZ acting on the code state does nothing because it's a stabilizer. So you just absorb this and remove it, and you're just left with the error itself acting on the state with an overall minus sign. So what we have shown is that the stabilizer acting on the error state is the error state with a minus sign, which means this is an eigenstate of the stabilizer with an eigenvalue -1, and that's exactly the syndrome. So the syndrome that we actually computed using the circuit turns out to be exactly the commutativity relation of the stabilizer with the error. And in the binary world, that means that if you have if you have the rows in the quantum parity check matrix, you can basically take the symplectic inner product with the representation of the error. Here it is EX and EZ. So you just take the symplectic inner product and you get the syndrome bits. And using this matrix, you can do using this relation. So overall, everything that we have seen can be kind of changed into the binary world. And that leads us to this definition of CSS codes, which I'm sure you saw in the previous talk. So I'll quickly go through the definition. So CSS codes are defined by a pair of classical parity check matrices that are orthogonal to each other. And so the quantum parity check matrix will have a block diagonal form. And when you compute the syndrome, like we showed in the previous slide, it will turn out that the first part of the syndrome only depends on the Z part of the error, and the second part of the syndrome only depends on the X part of the error. So you have actually two distinct syndromes for Z errors and X errors. And if the two errors are not correlated in the channel, then you can actually decode them independently. But on a depolarizing channel, you have to take into account these correlations. And then logical operators will basically be the vectors that are orthogonal to HZ and HX. And that's how we define them. So a nice way to kind of visually represent these is using this kind of ladder that I like to draw. So you have, say, two classical codes, CX and CZ, and these are the dual codes. So the parity check matrix of CX gives you X stabilizers here. The parity check matrix of CZ gives you Z stabilizers here. And then the logical operators that we have defined, the logical X and Z operators, come from this modulo space of CZ modulo CX dual and CX modulo CZ dual. And then you can put dimensions to all of this and calculate how many logical qubits you have. And we say that the quantum code, the CSS code, is LDPC if these classical codes CX and CZ are LDPC. And the minimum distance of the code, of course, is the minimum weight of a logical X and logical Z. So this is the kind of CSS formalism. Take a pair of orthogonal classical parity check matrices to construct quantum codes. And one of the famous codes is the surface code. So let's go through that. So the surface code is visually represented in this kind of square grid where it is kind of a tanagraph. So every circle is a data qubit. Every blue square is a Z-type parity check. By that I mean that this enforces the stabilizer Z, 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 Z acting on the 4 neighboring qubits. And then every red square is an X-type stabilizer, which enforces X, 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 X acting on 4 neighboring qubits. And you can check that all these stabilizers commute. So for example, if we take this X stabilizer and this Z stabilizer, clearly they overlap only on these two adjacent qubits, and therefore they will anti-commute twice, which means they commute. So all these X and Z stabilizers commute, and this defines a valid code. And then you can check that a logical X and Z operators for this code can be defined on on a vertical line or a horizontal line. So the vertical line here in orange, which is x acting on this circle, this circle, this circle, this circle, this circle. So it's a 5-qubit x operator that will actually flip the logical qubit. Similarly, a 5-qubit z operator acting on this line will act as a logical z operator. So this is a surface code of minimum distance 5, because that's the minimum weight of a logical operator. And it's conveniently defined on a square grid, which is nice for some types of hardware like superconducting qubits, because the only thing you need to engineer is nearest neighbor interaction. So think of this as the ancilla in a syndrome measurement circuit. Then you only have to talk to 4 neighboring qubits. You'll do 4 C0 gates and then measure this middle qubit to actually compute the syndrome for this stabilizer. And so because it only requires nearest neighbor connections, it's very convenient to build in hardware. So what happens when you have errors? So you can have, say, different kinds of errors. So for example, if you have a Z-type error on this qubit, naturally it will anti-commute only with the X-type stabilizer here, because this acts on these 3 qubits. But if you have a chain of Z errors, it will this X stabilizer will actually commute, because you have 2 Z-type operators, and they'll commute with this X-type stabilizer, which acts on these 3 qubits. Similarly, these 2 will commute with this stabilizer. So none of these 2 stabilizers will cause a -1 syndrome, but this end stabilizer, which only has 1 overlap, will anti-commute with the error, and you will get a -1 syndrome. So when you measure the syndrome, the only thing you will see is this thing is flagged. And then it's your job to figure out what is the most likely thing that happened. And here I've shown other examples. Let's look at decoding quickly for this code. So let's say we only look at these 2 regions where you have Z-type errors and you have 2 X stabilizers that are flipped. The way we decode is we first introduce these virtual checks, and you will see why we need them. So we first construct the syndrome graph, which is you collect all the X-type stabilizers that got flipped, and you put them here, and you then also put these virtual checks, and you draw edges between all of these, and the weight of the edge is the minimum number of qubits you have to pass to go from one stabilizer to the other. So for example, if you take a path from this stabilizer to this, you can go all the way down and then turn right, and you can count that there are 6 circles, and you can also go this way and down. That will also involve 6 circles, and any other path will have more circles. So the weight is 6. And so this basically denotes that if all these 6 qubits were in error, these 2 stabilizers will be flat. And these weights do the same thing, but by matching with this virtual check. So this virtual check exists because you could also have just one error here, which will only flip the syndrome. And so, but it needs to have a match. So we do this virtual check business. And then what you run is this minimum weight perfect matching decoder. What it does is it tries to match every node in this graph to exactly one other node in such a way that the sum of the weights of the pair nodes is the smallest. So in this case, if you match the smallest weight matching, the minimum weight matching would be to match this with this virtual check and this with this virtual check, because the sum is only 3, and any other pairing will give you a larger sum. Unfortunately, though, this is correct decoding because we only have one Z error here and we matched correctly. But this one, the channel actually introduced 3 errors, whereas your matching will do it on the other side because it only involves 2 errors, and it's kind of a memoryless channel. And what you end up doing is that the actual error followed by your correction, your estimate of the error, will cause a logical Z operator to occur, which causes a logical error. So of course, like just in classical codes, there are cases in the quantum codes also where it's beyond the capability of the code to correct these errors. So that's how the surface code works. And if you simulate the surface code with a range of physical error rates, these depolarizing error rates, for different distances. So this is, like I said, this has distance 5. You can go from distance 3, 5, 7, 9, 11. And if you run this decoder, and this time to failure is basically kind of an inverse of the logical error rate. So it just says for how long are you able to keep the logical qubit from being in error. You will see that you will get these plots and you get this threshold phenomenon. So this is kind of the inflection point. So if you're on the left of this point, if the physical error rate is lower than say 15.5%, then you see that if you increase the distance of the code, then the time to failure increases, which means you preserve the information for longer. Whereas if the physical error rate is larger than the threshold, then actually increasing the code distance makes things even worse. So the existence of a threshold tells you that the code is stable, and if you're on the right side of the threshold, increasing the size of the code actually improves the performance. And so this is what we look for in performance curves.
So just a doubt here. So
yeah,
the inflection point is same for all distance, right? It's independent. It's same for all the distances.
No. So the inflection point is defined for the family. It's not for individual codes. So you plot for all distances, and you see if they meet at a common point. There are families of codes where if you keep increasing distance, you don't get a threshold. So the threshold does not always exist, but when it exists, it is a phenomenon it is a property of the family for growing distance. So it's not tied to individual distances. It's actually plotted for the family.
So is the inflection point analytically derivable, or is it just due to simulations we plot and see?
Yeah, great question. So in classical codes, there are, like we know, we can do like density evolution and these kind of analysis. But in the quantum case, for example, for the surface code, people have been able to predict this threshold using statistical physics connections. But for many code families, they are computationally derived. It's pretty hard to analytically find them because the graphs of quantum codes have lots of loops. So a lot of the density evolution type techniques we use in classical codes, which rely on a tree, like a locally tree-like assumption, breaks. And this is why it's hard to do analytically derive them. So typically we do Monte Carlo simulation.
Okay, thank you. So Monte Carlo, what is the tool that you use for this Monte Carlo simulation? What would we do?
We have done it in MATLAB, C, and recent days. I think in recent years the popular tool is STIM, STIM, which is a Python-based tool to do kind of circuit level noise simulation.
Okay.
Where by circuit level noise, I mean that there are not only errors on the data qubits, there can also be errors on the CNOT gates, on the measurements. Like every circuit component can have an error. So you sample errors on all of them, and then run decoder on them.
So these noise points are randomly generated, like from any distribution? Or?
Yeah. So typically you assume like an IID depolarizing channel for all the qubits, but for also all the gates that you have. And you sample errors and propagate them, find the syndrome, run the decoder, and see if you corrected them.
Okay, thank you.
Yeah. All right. So there are generalizations of these connections. So the surface code has been generalized by this hypergraph product construction by Tillich and Zimor about 15 years back. So I won't go into the details. So I just wanted to have it to show that it is possible. So formally, this will be a graph product of two classical Tana graphs. And I'm sure you looked at this in the previous talk, so I won't repeat it. Again, you can run these iterative decoding algorithms on these Tana graphs with some caveats. For example, there is no received vector, there is no y, like I said before, so you have to compute the syndrome and use the syndrome to do decoding. And so when you do these message updates, whether you do parallel or serial message updates makes a big difference. And then these can affect how error flows occur, whether the performance kind of flattens out at some low physical error rate, or if it keeps going down. So here is an example where with a parallel schedule, it flattens out, but with a serial schedule, I think there is still a floor, but it's much smaller. There is degeneracy, which means that two different errors can have the same effect on the code if they differ only by a stabilizer. That's a uniquely quantum property. So all of these things you can exploit for building decoders. And so these are all like some of the recent work that has happened. There's even more. This is not exhaustive. But we have very good codes, but there are still a lot of challenges. So these surface codes are called topological codes, and a lot of things are known about them, but they're not very scalable because they have a large overhead. They always encode one logical qubit into a large number of physical qubits, like this lattice. Whereas optimal quantum LDPC codes exist today, and they have optimal rate and distance parameters. But how to do logical gates on them, and they have many long range connections. They are not kind of nearest neighbor like this. And so how to overcome that is a big question. So I'll show you a glimpse of what people do these days at the end. Okay, so in the next 5 to 8 minutes, I want to go over some fault tolerance ideas, and then we'll wrap up. Any questions? Okay, now I will continue. Okay, so recall that we defined a universal set of gates, and we have seen how quantum error correction is defined, how stabilizer codes are defined, how do you actually measure the syndrome in the lab, and how you can simulate these using this kind of binary notation. So the main missing piece is how to do computation. So how do you take logical gates and translate them into fault tolerant physical gates? Now, before we look at exactly fault tolerance, let's see what the goal is. So when we say a circuit is fault tolerant, it means that if let's say you have a single error correcting code. So let's say you have the SHAR code, it's 913, so you can correct a single error. So fault tolerance for the SHAR code means that any circuit that you construct and claim to be fault tolerant should satisfy the property that if exactly one fault happens, which means a single data qubit could be in error, or a single measurement could flip, or a single CNOT gate could fail, or a single Hadamard gate could fail, and so on. So any single fault that happens in the circuit block remains correctable at the end of the circuit. Basically, we don't want faults to propagate, right? So if you have circuits constructed in such a way that a single error propagates through the CNOTs and kind of spreads to all qubits, it's kind of like a pandemic. So you don't want that to happen. You want errors and faults to be localized and be controlled. And that's what we mean by fault tolerance. So let's look at a concrete example. Let's say I take the Steen code. So we have already seen Peter Shor's code. This is Andrew Steen's code. So we all know the classical Hamming code. This is a parity check matrix. And you can define a CSS code using this because H transpose is 0 and it satisfies the CSS condition. So this is a valid stabilizer matrix. And the logical poly operators in this case will just be X and Z acting on all the qubits. Now I want to do a logical Hadamard on this code. So which means I'm encoding one logical qubit to 7 physical qubits. And I already know how to do X and Z on the logical qubit by these physical operations. Similarly, I want to know how to do Hadamard on the logical qubit by a physical operation. So we know that the Hadamard changes X to Z and Z to X by conjugation. And it turns out that in this case, which means that in this case, we want a physical circuit that conjugates the logical X operator, this string, into the logical Z operator, which is this string, and vice versa. And it turns out that beautifully for this code, the logical Hadamard is just a physical Hadamard on every physical qubit. And this is what we call a transversal operation. Transversal means the operation is the tensor product of individual qubit gates. They don't always have to be the same, but in this case, it's all Hadamard on every qubit. And you can verify easily that, we know that every H will conjugate X to Z. Therefore, all these 7 H's satisfy both of these relations. They change logical X to logical Z, logical Z to logical X. Therefore, this is a valid logical Hadamard. So it kind of works out easily, but for more general codes and more general operations, it's not trivial to find these solutions. And so we built an algorithm to do this. I'm not going to go into the details, but at a very high level, you can input any k-qubit Clifford circuit on the k logical qubits of the code, described using a sequence of Hadamard, phase, C0, and I didn't tell you, but there's also control Z. If you describe a circuit like this and you input to the algorithm and you define the code and its logical poly operators and initialize the algorithm, it actually gives out all possible physical Clifford circuits that realize this logical Clifford circuit on the code. Because you have redundancy in the code, there are many different physical circuits with the same logical action, right? There is this kind of degeneracy in physical solutions, and it actually can compute all the physical realizations. There's a MATLAB implementation on GitHub here, and there is a Python implementation by my former student here. So that's one way. I mean, the outputs are not always fault tolerant, but it does search for all solutions. Now let's try to, so we saw that we have to do Hadamard, T, and C0. So let's look at the T gate. So the T gate, of course, I'm taking the same code. And like I said, T is not Clifford, so it actually conjugates X to something that's not poly. It's a linear combination of polys. In fact, this is actually Clifford. And so you want the logical T to satisfy these relations. Unfortunately, though, we don't get lucky with this code. If you just do T on all the physical qubits, it does not do what you want. So this trick doesn't always work, this transversality trick. It needs specific type of code structure, which I'll talk about next. And there is a fundamental no-go theorem called the Eastern null theorem, which says that there is no error correcting code where all the Clifford and non-Clifford gates like HT and C0 will all be transversal, right? So Steen is an example of that. So Hadamard is transversal, and the C0 will also be transversal. I'm not going to show it, but the T is not. And so a beautiful trick to get around this problem is called magic state distillation. So what you do is, instead of trying to implement the T gate on a code directly, you distill magic states. So a magic state in this case is this get T state, which is T acting on this superposition. So what you do is you physically prepare noisy states, these T states, 15 of them, and you can use a triorthogonal code, which is defined in this paper, to kind of measure stabilizers and clean up errors on these noisy states. And what you end up getting is one better quality T state as the output. And then you can run this many times. You can run this 15 times. You'll get 15 better quality T states. And you can take those 15 and feed it again as input. And if you do distillation, you will get an even better T state. So you keep doing this distillation routine until your output quality is good enough. It meets some criteria that you have. Once you have that, you encode it into, say, the surface code, if you're doing computation using the surface code. So you have a surface code now encoding the T state. And let's say this is the actual circuit you want to implement for your algorithm. It's a sequence of Hadamard and T, and you know how to do the Hadamard, let's say. You want to do the T state now. The trick is to use this magic state injection circuit, where instead of doing the T gate directly on the state, you can actually use this distilled magic state, and you can interact it with your actual code state and do these kind of operations. And note that these operations only involve Cliffords. So T square, like I said, is the phase gate, and X is the poly. So and this is just a poly measurement. So this is just a Clifford circuit, where by injecting this T state, you can interact it with your actual code state and actually implement the logical T. So people get around this problem of implementing the logical T directly by using this magic state distillation and injection, which is a very beautiful idea. And I would say like this is kind of the mainstream in fault tolerance today to get to universal computation. And so a famous example of this triorthogonal code is this 1513 code, which is constructed using classical Reed-Muller codes. So if you're a coding theorist who is familiar with Reed-Muller, this is a very beautiful code to look at. And we kind of looked at a more general question. We asked, what are the most general codes that admit this kind of transversal T? So the property of the 1513 code is that if you do T on all the physical qubits, it actually does a logical T. Remember, for the Steam code, the logical T was not equivalent to T on all the physical qubits, but for the 1513 code, it is. And in our work, we asked what are the most general codes for which these T on all the physical qubits preserves the code space. And we answered that in these papers. And we introduced this family of code, this construction called CSST, which is an extension of CSS. You take a CSS code and add more constraints to the code words of the stabilizers. And that kind of guarantees this property that transversal T does a logical T. Okay, with that, I'm going to wrap up this talk very soon. So we have seen, we've reviewed classical error correction. We looked at the basics of quantum computing and quantum error correction. We saw how quantum error correction can be connected to classical error correction. And then we looked at fault tolerant gates. And today I'm going to tell you how people are thinking of building these computers. It's only two or three slides left. Daniel Litinsky wrote this wonderful paper several years back, where he showed that any quantum circuit can be recompiled into just a sequence of Pauli measurements on qubits and these pi/8 or non-Clifford Pauli rotations. And he showed how these non-Clifford rotations can also be implemented using Pauli measurements followed by some Clifford operations. And note that for implementing this non-Clifford operation, you have a magic state as input, and this magic state is distilled using, say, this 1513 code that I showed you, using a magic state distillation kind of factory, and all of this is turned into just measurements. And so this is done using something called lattice surgery, which I didn't have time to talk today. And people have extended this lattice surgery idea to more general LDPC codes in this paper. And in the last 1 or 2 years, there's been an explosion of papers on these logical measurements on LDPC codes. And IBM released their architecture recently, which they call the bicycle architecture, using this so-called gross code, which is a bivariate bicycle code. And they have this kind of architecture principle where they have multiple nodes, each consisting of this gross code, and they have these ancillary qubits that help interact between different modules. And then they have magic state factories, which prepare this T state. And then you can use measurements to also inject these T states into the computation. And this is how they're thinking of actually building their computer. You can look at more details in this paper. So hopefully that gave you an idea of how quantum error correction works and how fault tolerance works. Of course, there's many details that we couldn't go into today, but hopefully this gives you enough information to get started in this field. These are my wonderful PhD students working with me, and I thank all my sponsors for all the support over the years for my research. Thank you so much. I hope you found this useful.
Very good. So I just have one question.
Yeah.
So in the classical communication, we have this lots of interest in using machine learning for coding and end-to-end training, autoencoders on that. Is there a similar interest in the quantum code field also?
Yeah. So I mean, the main issue is kind of scalability, but I do see many machine learning based decoder papers coming in the recent years. So I think people are actively working on that. And people have also used specifically reinforcement learning to kind of build decoders, but also to learn noise. So sometimes like noise in the hardware is more complicated than the depolarizing channel. And so if you want to really learn the noise, you have to come up with some end-to-end machine learning kind of model. So I think, yeah, there is definitely active research on that topic.
Thanks a lot. Thank you. Thanks for the talk. Thank you.
Sure.
Have a good
Any
day.
other questions?
There was one in the chat window long back. I think you answered it.
I think I did. Yeah.
Yeah. About the IXYZ. Yeah.
Yeah, and feel free to, I think you put my email in the, but if you find our university website, you'll find, or email in the chat. Feel free to email me if you have further questions.
Yeah.
Thank you so much for having me, Dr. Sudarshan.
Thank you. Thanks a lot for your time. Thank you.
Yeah. Good night for everyone. Bye.
Yeah. Good day. Yeah. Participants, I have put the attendance and the feedback link, so you can fill in there. Okay. So on Saturday, we'll continue tomorrow, Friday. On Saturday, the session starts at 2 o'clock. We have 3 sessions on Saturday, and at 6:30 there'll be a test. Okay, so but that won't be very difficult. Just like the pre-assessment, that will also be simple only. It's mandated by AICTE, so there'll be a test on